Today's today's speaker is Yuta Mizuno from Hokkaido University, and his title is Enumeration Algorithms for Combinatorial Problems using Ising Machines and their application to chemistry. Yuta, please start.
Okay, so can you see my slide? Not yet.
Yes.
Maybe. And okay, so thank you for kind introduction, Kadawaki-san. So I'm Yuta Mizuno from Hokkaido University. So first of all, so I would like to thank the organizers, especially for Professor Warburton and Ms. Shani for giving me this opportunity to share our recent research on enumeration algorithms for combinatorial problems using Ising machines and the application to chemistry. So before going to the today's main topics, let me introduce the research background. So basically, I'm a theoretical chemist and have studied applications of quantum or Ising computing to chemistry in recent years. So this schematic figure shows the my research project overview. So since the inception of modern chemistry in the 18th century, scientists have designed and discovered numerical chemical reactions. And these discoveries are recorded in chemical databases, which can be represented by gigantic chemical reaction networks like this. And so this collection of chemical reaction data is a big data in chemistry and have experienced rapid growth. Furthermore, the emerging technologies such as robotic synthesis, AI machine learning, and quantum chemical calculation enhance automatic chemical reaction exploration. Moreover, quantum computing is also expected to enhance AI machine learning and quantum chemical calculation. So these emerging technologies will speed up or accelerate the exploration of novel chemical reactions, leading to rapid increase in the data size of chemical reaction databases. So given the availability of these big chemical databases, so it is desired to consider how to exploit these big data for chemical sciences and engineering. On the exploiting side, there are several important significant problems, but with some computational hardness, such as pathway finding in chemical reaction networks and atom-to-atom mapping in chemical reactions, and stochastic kinetic analysis of complex chemical reaction systems. So also quantum computing for exploration of novel chemical reactions have been intensively studied. Quantum computing for exploitation of exploiting these chemical big data have little attention. So therefore, in my project, we aim to develop quantum or Ising computing frameworks for these problems to accelerate the exploitation of chemical big data. So for these three topics related to the exploitation of chemical big data, we have developed quantum or Ising computing framework. So for the first topic, an Ising computing framework for chemical pathway finding, such as synthesis planning, has been developed. And the performance of the proposed framework was evaluated using a DF advantage quantum annealing machine. So I think so. This topic is also relevant to the background of this seminar's audience. So if you are interested in these topics, please check also this paper. And the second topic, atom-to-atom mapping, is closely related to today's main topic. So I will explain this topic in detail in the next few slides. And the third topic is stochastic reaction kinetics. The analysis of stochastic reaction kinetics is important for understanding microchemical reaction systems such as biological cell. And stochastic reaction kinetics is described by an exponentially high-dimensional linear differential equation called chemical master equation. So it is hard to simulate on classical computer. In contrast, quantum differential equation can solve such high-dimensional linear differential equation exponentially faster than classical algorithms, but they just generate the quantum states that encodes the time series data. So how to extract essential dynamical information from these quantum states is a critical problem. To address this challenge, we devised quantum dynamic mode decomposition algorithms presented in this paper. Okay, so let's move on to the atom-to-atom mapping topics. So atom-to-atom mapping problems is formulated as follows. Find the correspondence between the atoms of reactants and products in a given chemical reaction formula. Suppose we are given this chemical reaction formula, and we may think, so what is the mechanism of this chemical reaction? And if each atom is labeled and each number represents the identity of atoms on both sides, then we can easily understand. So this reaction mechanism is that the bond between atoms 2 and 4 is cleaved, and the bond between atoms 2 and 7 is formed. So in this way, the atom-to-atom mapping is a procedure to give such labeling to each atom. So this atom-to-atom mapping problem is very essential for recognition of reaction mechanisms. And these atom-to-atom mapping problems can be modeled as an NP-hard combinatorial optimization problem. Specifically, this problem can be formulated as follows. To find the atom-to-atom correspondences that minimize the number of bond cleavage and formation during chemical reaction. For example, in this case, only one bond broken and one bond formed. So generally, in a simple chemical reactions, the number of bond cleavage and formation is not so much high. So this assumption is valid for most chemical reactions. So to solve this combinatorial optimization problems, we can annotate this chemical reaction formula. But this is NP-hard problem, so it takes very long time, long computation time. So usually the existing atom-to-atom mapping tools employ some chemical heuristics or machine learning techniques, but that these solvers strongly depends on the pre-existing chemical reaction data or some chemical reaction rules. And they have some bias to the common reaction pattern. So to avoid this problem, we want to develop the rule-free atom-to-atom mapping tools by applying Ising computing techniques to this NP-hard combinatorial optimization problem. But in the application of Ising computing to this problem, there's one challenge. That is, so in atom-to-atom mapping problem, it often has multiple optimal solutions. For example, for this chemical reaction formula, there's two possible mappings exist. And nowadays, we know, or chemists know, this above mechanism is correct, but about 100 years ago, no one knows which mechanism is correct. So if we have multiple mappings, so we may think which of these mechanisms is correct, but we can test this hypothesis. Actually, in about maybe 90 years ago, some chemists conducted isotope labeling experiment to determine which mechanism is correct, and they conclude that this mechanism is correct. So in this sense, if our framework only generate one single solution, it is possibility that our framework miss this ground truth mechanisms. So in this problem, so enumerating all plausible mappings is highly desirable. So this problem settings motivated us to develop enumeration algorithms for combinatorial problems using Ising machines. This is today's main topic. And today's talk is based on these preprints, and you can access this preprint by this QR code. Okay, let's move on to the main topics. So first, introduction. So our research goal is to develop enumeration algorithms for combinatorial problems, that is constraint satisfaction problems and combinatorial optimization problems, and using Ising machines. So enumerating all constraint satisfying or optimal solutions provides flexibility in decision making, as we saw in the atom-to-atom mapping problem case. But combinatorial problems and their enumeration versions pose significant computational challenges. And the Ising machines are specialized devices designed to efficiently solve combinatorial problems, including quantum annealing and quantum approximate optimization algorithm and simulated annealing, etc. And more precisely speaking, Ising machines are specialized to sample low energy states of Ising model. So typically, an Ising machine samples low energy solutions in a stochastic manner, for example, following Boltzmann distribution. And so if we repeat the sampling, maybe infinite time, maybe we can collect all target solutions, that is constraint satisfying solution, and or combinatorial optimization, combinatorial optimal solutions that is correspond to ground state of Ising model. But in practice, so when should we stop the sampling? Even if we can repeat infinite time the sampling, then we get the all solutions. But in practice, we need to stop some appropriate timing. So the main research question in this study is when should we stop the sampling? To derive appropriate stopping criteria, here we introduce sampler models that mimic the or idealize the existing Ising machines, such as noisy quantum annealing machine and simulated annealer and QAOA and coherent Ising machine, etc. So the common property of this Ising machine that the low energy solutions are sampled more frequently, and equal energy solutions are sampled with equal probability, like this. And clearly, a Boltzmann distribution or Boltzmann sampler satisfy this condition. So, and this we call the sampler satisfying this condition as energy ordered fair sampler, and energy ordered fair sampler forms the superset of Boltzmann sampler. And there's several literature that reports that for example, QAOA, noisy quantum annealing machine, and the simulated annealer empirically mimic or follow the approximate Boltzmann distribution. So we expect that the actual Ising machines sampling property do not deviate so much from this assumption or sampler model. So to explain or derive the appropriate stopping criteria, first we consider very simple case, and that is a well-known problem in probability theory called coupon collector problems. So coupon collector problems asks how much is the number of samples T necessary to collect all n distinct items by fair sampling. For example, the n equals 3 case, so we get green, blue, red, so that the necessary number of samples T goes to 4. And in the another trial, T equals to 6. So T is a kind of random variable. And in general, it is known that this random variable T, or necessary sampling times, follows this probability inequality for arbitrary positive number epsilon less than 1. So this equality implies that if we stop the sampling this time, then we get all solutions with a success probability exceeding 1 minus epsilon. So the failure probability is bounded by this epsilon. So this timing can be used as a deadline for collecting n distinct items, ensuring the failure probability of enumeration below epsilon. But that situation is very ideal situation because in the context of Ising machine sampling, and that fair samplings correspond to the situation that we know the minimum energy and the number of minima. Because if in the fair sampling, in this case, the sampler only sample the target solutions, but in reality, or in our context, the Ising machine can also sample non-target solutions or or excited states. But if we know the minimum energy value, we can reject the excited states during sampling. So virtually we can construct sampler that samples only target or ground states. And in the coupon collectors problem, there's an assumption that we know the number of distinct items in advance, but in reality, we don't know the number of minima in this sampling. So we need to extend this coupon collectors problem theory by relaxing these assumptions. And first, we devised algorithm one where this assumption is removed. But to compensate the lack of information about the number of minima, the deadline is extended slightly, and this kappa 1 can be considered as correction factors compensating for lack of information. And the definition of kappa 1 is this one. And so today I have no time to explain the details derivation of this formula. But if we set the kappa 1 to this value, then we have a theoretical guarantee that the failure probability of enumeration is below epsilon. And the next algorithm in algorithm 2, we also relax the assumption about the minimum energy. And in this case, the correction factor changed to kappa 2, and kappa 2 is defined like this, and kappa 2 is slightly, not slightly, kappa 2 is greater than kappa 1 to compensate additional lack of information. Okay, next, I will explain the details mechanism of our algorithm. And here, I need to acknowledge that this algorithm is inspired by an algorithm proposed by in this preprint, but the details and the correction factor kappa is novel point in our study. So in this case, we know the minimum energy of Ising model. And in Ising computing cases, so for example, the constraint satisfaction problem is often formulated using penalty terms. And if penalty terms is equals 0, then the solution is target solution. That means, so in most constraint satisfaction problems cases, we know the ground state energy. So this algorithm 1 can be applied to constraint satisfaction problems. And first, we sample this solution, and this value indicates the energy of this red state. And this energy is greater than this value, so we discard this one. And so next sample is also discarded, and next sample is also discarded, and we get this one, and this one is one of the minima, so we collect this one, and we set sample count 1, and now we have a one solution. So our next goal is to collect two distinct solutions, and we set deadline to 11, and this deadline is calculated by this formula. And continue to sample, collect this green one, and skip to this deadline. And at this deadline, we have two distinct solutions. So this goal attained. So we continue the sampling. Then we update the goal to collect three distinct solutions, and deadline is now update to 18. And skip to 18. Then at this deadline, so this goal is not attained, so we stop the sampling. So in the algorithm 2, now we don't know the minimum energy. So first we sample this one, and we record this energy value as a current minimum energy, and we tentatively collect this solution. And set sample count next to goal deadline, and deadline is now calculated by this formula. And sample second one, and collect this one, and sample this one, and sample this one. And then now we get a better solution. So update this current minimum to 0.0 and discard corrected solutions and added this better solution to this corrected solution set. And we continue to sample this one, this sample, and correct this one. And next, this one is sampled. But now this energy value is greater than the current minimum energy. So we discard this one. Also, we discard this one and skip to this deadline. And at the deadline, two distinct solutions already corrected. So we continue the sampling. Then update the goal and deadline and skip to this one. And here, this goal have not attained at this deadline, so we stop the sampling. This is a mechanism of our algorithm. So next, we show the numerical demonstration. And this numerical demonstration result is also presented in this preprint. And here we consider maximum clique problem. The maximum first, the clique is a subgraph where all vertices are adjacent to each other, and the maximum clique is the largest cliques. So for example, given this graph, then maximum clique is one of the maximum clique is this green one. And this maximum clique problem can be formulated as quadratic unconstrained binary optimization problems like this, and the details for the details, please see this Lucas paper. And we generated 100 Elders-Renyi random graphs for several different graph densities. And we solve each problem 100 times using algorithms to combine with simulated annealing with the failure tolerance epsilon equals 0.01. And this figure shows the computation time, average computation time of our algorithms indicated by blue one. And also this figure shows the computation time for a conventional exact algorithm for maximum clique enumeration indicated by red points. And we can see that for large dense random graphs, our algorithm outperforms the conventional exact algorithms in terms of computation time. Next, we examine the success rate of our algorithms. So, and we found that the success rate of our algorithms tend to decrease with graph density. This figure shows the histogram of the number of successes. And so statistically, now we set the failure tolerance epsilon equals 0.01. So our expectation is that our algorithm succeeded in finding all maximum cliques with probability greater than 99%. So this number of successes should be close to 99 or more. And this result is compatible with our theoretical analysis in a statistical sense. But this case, some cases may incompatible with our theoretical guarantee here. And in this case, these low number of successes may deviate from our expectation. But this is not the but this is due to the unfairness of sampling in this case. So here we examine the fairness of the ground state sampling, and this chi-square test is commonly used to test the fairness of sampling. And if this p-value is equal to 0, then it's fair, and if tends to 0, then it can be considered as unfair. So you can see that so if the p-value is significantly lower, then the success rate is also lower. But if the p-value is greater than 0.05, all cases are consistent with our theoretical expectation. That is, the number of successes is greater than 99. And this panel shows the ratio of maximum probability and minimum probability of ground state sampling. And if the ratio is 1, the sampling is fair. But if the ratio is large, then the sampling probability deviates from the uniform distribution largely. And we can see that there's some linear negative correlation between the success rate and this ratio. So this indicates that so we can maybe I expect we can extend our algorithm incorporating this parameter to indicate some deviation from the ideal fair sampling. Okay, finally I will explain the result of application to atom-to-atom mapping, and this chemical part is now has been accepted in Journal of Chemical Information and Modeling and will be published soon. But now, if we want to release some preprint, please access this DOI. So atom-to-atom mapping functions can be reduced to maximum clique problem, and the reduction to maximum clique problem is very complicated. So please see our manuscript. So I will skip this part now. And we developed this kind of framework for atom-to-atom mapping. The input is chemical reaction formula, and this atom-to-atom mapping problem translated into the Ising model, and using our algorithm 2 plus simulated annealing, we enumerate all ground states of Ising model. And applying post-processing, we get these atom-to-atom mapping, several atom-to-atom mapping. And this is an analysis of computation time. So for large size problems, our algorithm outperforms the conventional exact algorithms for maximum clique enumeration in terms of computation time. Even also for this chemical application. And this figure shows the chemical correctness of our proposed framework. So blue one indicate the number of correct mappings our proposed algorithm generated. And these two bars correspond to the different option for post-processing. So in this talk, please neglect this two bar. So please look at only this bar. And these gray bar correspond to the conventional rule-based or machine learning-based atom-to-atom mapping tools. And as we can see, so our proposed algorithm succeeded in finding the correct mapping assigned by expert chemists for all problems in the benchmark dataset, and which is comparable to the state-of-the-art atom-to-atom mapping tools, RX and Mapper. Furthermore, our proposed algorithm found a chemically plausible alternative mapping in this chemical reaction, and which is missed by other conventional methods. In this reaction, so other conventional method only generate this mapping, and this mechanism is somehow common in organic chemistry, but some literature suggests that this kind of mechanism also happen in this particular context, and our algorithm enumerates these both two plausible mechanisms, but the conventional method only generate this one because they are biased to the training dataset and most common reaction patterns. So in this sense, so in atom-to-atom mapping problem, enumeration is crucial to avoid the missing the chemically plausible hypothesis. So this is a conclusion, and yeah, we have developed enumeration algorithm for combinatorial problems using Ising machines, and they incorporate appropriate stopping criteria for sampling. And there is a theoretical guarantees that the failure probabilities below epsilon provide that lower energy solutions are sampled more frequently, and equal energy solutions are sampled with equal probability. And our algorithms too outperforms the conventional exact algorithm for maximum clique enumeration in terms of computation time for dense random graphs and atom-to-atom mapping problems. And this is acknowledgement. So this work is done with collaborating with Mr. Muhammad Ali. He is my PhD student, and Dr. Seiji Akiyama, Dr. Yue Nagata, and Professor Tamiko Masaki. And this work was supported by these funding. Okay, so thank you for your attention, and sorry for the exceeding the time. That's all.
Thank you, Yuta. Great presentation. Any comments or questions? Okay. Okay. I will start. So we already know that the quantum dynamics, if you utilize the dynamics for optimization problems, just some kind of the bias of, I mean, the unfair sampling will occur.
Yeah.
But you tested with simulated annealing for this case, if I understand correctly. Even though you see the unfairness, kind of
Yes,
unfairness,
yes.
where did this came from?
Because so I'm not sure, but in this case, we use some geometric annealing schedule, and there's no, I, I think there's no theoretical guarantee that the sampling probability is close to
Mhm,
Boltzmann
mhm,
distribution,
mhm,
and maybe some particular state is the sampling probability of for some particular states suppressed. But to discuss the origin of this unfairness, I think we need to uh, analyze some energy landscape of for each particular problem cases.
mhm. So you mean even though that the simulated annealing or classical approach will have some unfairness,
Yeah,
or it depends
yeah,
on the detailed algorithm of the
yeah, or
annealing.
yes, and it depends on the problem and the parameter setting also. If we
Mhm,
use
mhm.
another annealing schedule, maybe we can get more
I
fair
see, I
result.
see.
Mm. But so important point is that even if the sampling is not exactly fair, our algorithms succeed more than
Mhm,
80%
mhm.
or something like that. That is the point.
Thank you.
Thank you.
Any other comments or questions? No. Okay. Thank you again, Yuta.
Thank you. We'll stop the sharing.